All right. It's always good to start a little lesson with a little Missy Elliott, right? All right, we're going to come back to that, and I promise you that's going to be relevant. I promise you a few demos in this video, and I'm going to start off with a question. The question is: suppose you play a recorded sample of a musical instrument, and you look at the spectrum. Then you play the sample backwards and look at the spectrum when it's played backwards. Does the spectrum change? All right. So think about that question for a second. Does the spectrum change when you play the sound backwards? And then does it sound the same when you play it back? All right. So before I do, before I talk about how this connects to Missy Elliott, I'm going to actually go back to the tones that we were listening to in the previous video. This is our trumpet, our violin, and our piano. Our violin, trumpet, piano. Okay. And I'm gonna let's start. Well, we'll start with the violin. If I start with the violin and I plot the spectrum, there's our spectrum. All right. I'm going to take my screenshot of this. Right there. Okay. And then I'm going to bring that spring. I'm just going to bring the screenshot up. Hopefully I can find it quickly. Go. Okay. All right. So there's the spectrum of the violin that I just played. And then there's a cool thing here in Audacity where I can reverse this. So I can reverse it. You see now it's that waveform is backwards. And I can, since it's backwards, I can analyze that, plot the spectrum, pull it up. All right, and so now we can compare this spectrum to the spectrum when it was played forwards. All right, so I'm just going to put them side by side. Okay, so putting them side by side, I hope it's obvious to you that the spectra are essentially identical. Not exactly identical, but they're very, very close to being identical. So there's a peak right here at this amplitude, and then the next peak is a little bit lower, and the third peak is a little bit higher than the second, but not as high as the first one, and then the fourth one is a little bit lower than the third, and the fifth one is almost as high as the first one, and the same pattern repeats over here. So what we see is that the spectrum did not change at all when we played the sound backwards. But why? Why is that? Well, remember, the spectrum is the recipe of all the amplitudes and frequencies that are in the sound. And just because we played the sound backwards doesn't mean that any of the frequencies changed at all. So reversing the sound, or in other words, changing the waveform of the sound, didn't change the spectrum. All right, but did it change the timbre? Does it sound different? So let's try this out. Let's play this. So this is the backwards violin. I'm just going to play this part right here. Did that sound different? It sounded a little different. Not noticeably different, but there are instruments in which the timbre depends way more greatly on the waveform than the violin, for example. And I have a different demo that I want to play for you and show you how that works. So I'm going to play. Here's this. This is all audio, so you just have to listen to it.
Effect of tone envelope on timbre. You will hear a recording of a Bach chorale played on a piano. Now the same chorale will be played backwards.
Okay, so the exact same sheet music is going to be used, but the performer is going to start on the last note of the sheet music and just play it in the reverse order. So starting at the end of the sheet music and playing backwards on the piano. So here's what that sounds like.
Now the tape of the last recording is played backwards so that the chorale is heard forward again, but with an interesting difference.
So, in other words, they put their thing down, they flipped it and reversed it. All right, so the melody was back to the original melody that we heard in the very first clip, but the instrument sounded way different, right? I think it sounds a little bit like an organ or something that's kind of like a keyboard synthesizer, but definitely doesn't sound like a piano. And this has to do with the waveform of the piano. So if I flip back to our other example, here's our piano sound. If I play that by itself, sounds like a piano. But if I reverse it, play it, doesn't really sound like a piano, right? So that's what's going on. And this brings us back to Missy Elliott and this part of Work It, which probably if you've ever heard Work It before, you know this. So the line right before that, let me work it. I put my thing down, flip it and reverse it. I put my thing down, flip it and reverse it. But what does that mean? Well, I took that next segment here, this part right here, and I actually reversed it. Right? I just put it in a different track and I reverse it. So I'm going to mute the song and play the reverse part of it right here, so you can hear it. Put my thing down, flip it and reverse it. Put my thing down, flip it and reverse it. So what Missy Elliott did was took the vocal track and actually reversed it and played it and laid it over the beat, and that's what it sounds like. So I thought that was a really cool use of this waveform dependence on timbre, or the timbre dependence on waveform, however you want to look at it, in this tune. And I hope you enjoyed it too. All right, so that's it for this. I guess I'll just make it official. This is going to bring us to the end of Conceptual Objective 13 and Conceptual Objective 14, and I'll have some practice stuff for you posted soon. All right, thanks.